Okay, guys. We had left off on page 56 where we had discovered that the integral of a complex function over a path could be path dependent. We did as an example. And depending on how we traveled from 0, 0 to 1 plus I, we got two different answers. But there was a theorem that said if we had one path but one parametrization and the same path but a second parametrization, that this would then be the same answer. So the parametrization of your path doesn't really matter. It's just that it has to step along the right path. So today we're going to define the length of a path by virtue of an integral. It's going to be the integral from A to B of the modulus of the derivative of the path over dt. Now, what we want to make sure is, first off, these are nice paths. We do this over a path which is what we call piecewise. Its derivatives are nice and connected, so we don't want jumps in them. So let's just take a very simple path. Let's take a path going from 0, 0, which is 0, complex, to 1 plus I in a straight line. Now, this parametrization we've done several times. Gamma of t is equal to t plus ti. And we're going to let t vary between 0 and 1. So we move from 0, 0 to 1 plus I in a nice, smooth process. So using this definition, I would say then the length of our gamma would be the integral from 0 to 1. And we take gamma prime, we get 1 plus I, we take its modulus, dt, and now the modulus 1 plus I is square root of 2, times integral of dt from 0 to 1, which is root 2t evaluated from 0 to 1, which is root 2. And that's exactly how long that path is. Now, it seems very reasonable then that we should do a complex integral that maybe it looks a little bit harder. So, let's do this integral. Let's go around some circle of radius r in the complex plane. Well, we know there's a very nice definition of this. We want the modulus of z to be equal to r. Well, if we write z in polar form, the r goes in front and e to the I theta goes here. And if we let theta vary between 0 and 2 pi, well, that's the unit circle. So here the parametrization is over theta. We've been using t's, so let's write it that way. So now we have a gamma going through time with this path that describes the path that we want to do. And it actually goes counterclockwise. So let's see how long that path is. Well, the formula says that we want to integrate over the period that defines the path the modulus of gamma prime of t dt. So that's a real number. The derivative of e to the it. Derivative of e to the it will be I e to the it. And now, when we integrate e to the it, after taking its modulus, well, modulus 1, modulus r, modulus 1, we get 2 pi r. Well, that's really nice. It means that the path length works wonderful in the complex plane and that our functions are behaving quite nicely. Now, because of the fact that complex integration is almost exactly like real integration, since we've defined it as a path integral, it'd be very reasonable for us to ask the following question. Suppose that integral that we integrated from here to here, what happens if we had integrated it this way? In the real line, didn't we have it when integrated from a to b some function that if we switched it from b to a, that these were probably negatives of one another? Well, let's just check it out with that original integral we did. How do we go from 1 plus I down to 0? Let's find a gamma. So let's do gamma 2 of t. Now I'd like at t equal to 0 to be here, and at t equal to 1 to be there. So that's the interval I'd like it. So if I start at t equals 0, I'd like a 1 minus t plus a 1 minus ti there. So I'm at 0, then I'm at 1 plus I, and when I get to 1, I'm at 0 plus 0i. That seems to work. So if we did this integral now, let's find its length, the integral of 0 to 1 of the absolute value of 1 minus t plus 1 minus ti prime dt. So the derivative of this will be minus 1 plus minus I modulus dt, which will be, again, the square root of 2 dt, and we'll get the same value. So the length is not affected by the direction of the integral of the path. Well, that's kind of nice to know. What happens if we do a function, though, rather than just doing the path length? So what happens if we're integrating some function over gamma, and then we run this function backwards? So first off, let's have the notation that if gamma of some a is equal to z naught, and gamma of some b is equal to z1, and a is less than or equal to t, less than or equal to b, but gamma of, let's call that 1, gamma of 2 is gamma of a is equal to z1, and gamma of 2 of b is equal to z naught, a less than or t less than or equal to b, and all values of gamma of 2 of t are equal to some gamma of 1 of some t prime. In other words, there's gamma 1, starts at z naught, and goes to z1 over t equals a to t equals b. Gamma 2 does it the other direction. Well, it seems very reasonable that when that happens that we should call gamma 2 minus gamma of 1. That's a reasonable, good definition. Well, I wonder if there's a way to unwind time without having to save so much. Well, let's try this. Let's define a gamma 2 to be the original gamma with a plus b minus t, and we take a look at this. So if we start at a, gamma 2 of a, well, a minus a will be 0, will be gamma 1 of b. Oh, that's what's happening up here. And if we look at gamma 2 of b, well, b minus b leaves the a, so gamma 1 of a. So where one began, the other one's end, where one ends, the other begins. And now lastly, are all values of n equal to some other t? Yes. Gamma 2 is defined by values of gamma 1. So what this does is it runs time backwards. Here is a standard way in which to understand what minus gamma means. It is gamma of a plus b minus t. That runs something backwards. Now, we saw this here. Why are we able to write this down so easily? Well, the answer is that's minus gamma of 1 by that definition. Okay, so now, what happens now when we integrate a function, and then we integrate a function over gamma, and we want to compare these two? Wouldn't it be nice to know that it behaves in the same way that the real integrals behave? So let's take a look at that. Well, let's do an integral over minus the curve gamma of some function f in the complex plane. All right, by definition, the function is going to be integrated in the following way. First, we have to put in the gamma of t, and then we have to put in the gamma of t prime dt. That's the definition of an integral f over a path called minus gamma. But I know what minus gamma is. Minus gamma is just gamma of a plus b minus t. And minus gamma prime is gamma prime a plus b minus t. But the derivative of the inside for the derivative of gamma prime produces a minus 1 dt. So there's the chain rule on minus gamma of t's derivative. Well, I'm going to pull that minus 1 out, and what's left, oh, and this integral is supposed to be from a to b. So what's left now is we have the integral from a to b of f of gamma of a plus b minus t gamma prime of a plus b minus t dt. And so now what we have to do is we just do a change of variable. So let's let s equal a plus b minus t, and ds will be minus dt. So now what are we going to get? Well, first off, when we change the variable, this is going to be f of gamma of s, gamma prime of s, ds, and the minus cancel, so that'll be a plus. But now, when it started at a before, it starts at b, because when you plug in a, you get b, and when you plug in b, you get a, so it goes in the opposite order. Oh, but that's minus, they're going to go from a to b of f of gamma of s, gamma prime of s ds, which is integral of gamma of f. And so we've just produced that the integral going in the opposite direction changes the sign. All right, well, that's very, very reasonable. What else can we get out of this? Well, we can do what's called path appending. We have a gamma 1 where a is its start point and b is its end point, and gamma 2 its start point for some other time t, let's say c, b is, sorry. So the next idea is path appending. So suppose we have an a time and b some time, and we have a gamma 1 here. And now at some other time, it doesn't matter when, time equals c, gamma 2, and some time equals d. So we've started at z0, went to z1. Some other time interval started at z1, went to z2. This is just one path. Well, it seems very reasonable then that we should be able to say that we're integrating over these paths. Now, some people like to put a circle plus there. Some people put a little circle there, but it's gamma 1, gamma 2. Whatever notation, I like the circle plus one, the book doesn't use it, of the function, is going to be first you do gamma 1, and then you do gamma 2. And since we already have the theorem that reparametrization doesn't change anything, we can view this as a single path through time. We can cut a long path and say, we'll do this one and this one. And so you can use whatever time parameterizations you like. This is a cut and clip process. It's often used in the opposite way. Somebody has a path that's like this, and you decide, nope, this one is easy to do, this one is easy to do, I'll do the integral in two pieces, and you do whatever parameterization you like. That's the most common use of this theorem. All right, so now the next problem is we're going to produce what's called the famous ML theorem. M means maximum and L means the length. So first off, if we start with a function and we're going to integrate it over a path, that results in a complex number. If we want to take the modulus of this looks a teeny bit funny. I mean, not wildly funny, it just simply says I'm taking the modulus of a complex number. But we've got lots of operations going here. We've got this idea of integration along a path and then the complex modulus of it. Turns out that we have some control on this. It's called the ML value, where M is the maximum of the function on gamma times, and L is the length of gamma. Wow. What would this analogous theorem be in the real plane? Well, look at the following. Suppose we have a function f, we have an interval from a to b. If we find the maximum value of the function on a to b, isn't it true that the integral is going to be less than the maximum value of the function times the length of ab? It looks like this is the upper Riemann sum of a complex integral, stated in a new name and a fancy process. Wonder if this thing is hard to prove. Let's give it a shot. Let's just follow, as we say, let's follow our nose. So first off, in order to do this, I'm going to start with, I know my answer is a complex number, and using the right form of a complex number is very useful. So I'm first going to identify that that's a complex number, and whatever the answer is, I can write it as r times e to the I theta. And theta is officially the argument of that big answer, the argument of the complex number called the integral of f over gamma. Well, that is the r then. So how about I write this? If we start with the integral over gamma of f is my complex number, which is r e to the I theta, which is called the argument of that number, we've just identified that r is this thing that we have this fancy expression for. So whatever that number is, its modulus is just the r of its polar form. So let me solve for the modulus. Now, that's an exact equality, and it looks kind of funny, but I'm now going to calculate it. So first off, it doesn't hurt to take this and say, I want the real part of it because it's going to be real, so I can put this in trivially. But I'm also going to put in the definition of this. So all of a sudden, I've said I know I have a real number as an answer because I took a modulus of a complex number. I know it looks like this because I wrote it in polar form and then put the unknown on the other side. Now put that value in there. And now what I'm going to do is I'm going to say, well, let's put this stuff on the inside. That's a constant because whatever the answer is, it's a fixed theta for that argument. So I'm going to move that inside, and I'm going to put the request for real inside because it can be. So I'm going to get real f. So we get this expression that at the moment looks pretty funky, but it's a real expression. So now I'm going to use the first theorem of Riemann sums, and that is that integral has got to be less than the maximum of the value, or I'm sorry, the modulus. So all right. Now, the modulus can be thrown cross multiplication, but this is of modulus 1. And so that e to the minus I theta goes away. Now, the integral over the modulus of something, I can bound that by the max of the function on gamma, because that's a real statement. But now here's the crazy part. That's the definition of the length of our path gamma. And we have what's called the ML inequality. Well, that's pretty cool. So, what can we do with this? Well, we know how to calculate paths. We know some things about antiderivatives and the other things. I'm just wondering, is it possible that this, could it be associated with antiderivatives, just like we have the fundamental theorem in calculus, that if I know that f was a derivative of something, then the integral of f should undo that, and I would get an antiderivative up to a constant. That seems like a very reasonable thing to do. So let's make the first definition. We call f is an antiderivative of little f if it equals this. Now, in general, we want to talk about differentiation in that topological sense of that we need space. We don't like derivatives on just a simple line. So for z's inside of some domain in the complex plane, and we want that domain to contain enough space so we can talk about this function being holomorphic. In other words, its derivative exists within a disk that lives inside of D. So we want D to be big enough to contain a disk that contains the z's inside of there. Those of you that have topology, this is an open set. All right. So if we define something to be an antiderivative, and then the next thing we want to do is find out how antiderivatives are going to be related to integration. Now, I am going to use a theorem that I'm not going to prove here, and that is that if I know something is a derivative, that I want this answer to be f of z. That's not a deep push. In fact, a lot of books work very hard to prove it. In other cases, books will work very hard on something called path independence, and when they're all done, they're going to finally prove this fact. we would like to start with this fact. This is not a graduate course in complex variables. So we're just going to assume that this is true, and we're going to get some very nice consequences from this. And that is unfortunate, but it would almost take a good 2 weeks to really do that right. So we're going to begin with that assumption. So here comes our first theorem. So if G is some domain inside of our complex numbers, and gamma is a smooth, that means differentiable path inside of G, and it has a parametrization okay, and we also are going to say f is any antiderivative of little f. What are we going to calculate? Well, we're going to calculate the integral over gamma of f. Well, first off, we know that since the derivative of this function on the path gamma must be f of gamma of t, gamma prime of t by the chain rule, then this, by definition, is f gamma of t, gamma prime of t dt, and so this is the integral of a derivative, and therefore the answer is the f. But now the strange thing is it's the a and the b, and the change of value gamma produces gamma of b minus gamma of a. And so we just come up with the fundamental theorem of complex integration. And that is, if you integrate along a path, if the function that you're integrating has an antiderivative, then it's the endpoint minus the starting point. This is beautiful. It once again shows that the concepts of extending the reals to the complexes, making the complexes functions behave like the real functions and their derivatives and their definitions, that everything that we've been seeing is consistent. Now, this means some of our integrals should be easy. Like, if we start with f of z equals z squared, and let's start at the point 1 and wander under some strange path over to 9 plus 2i. Well, you know that if we take f of z, which is equal to z cubed over 3, that f prime of z is z squared, which is f of z. And you happen to know that the quadratic, which we proved, is a very nice function. We can do the same proof on z cubed, that this is a holomorphic function in an entire complex plane. So guess what? The integral over gamma of z squared, why, it's just going to be f of the end minus f of the start. We don't even have to know the path gamma. So the analogous thing is that when we do an integral from a to b of a function f, to get that answer, we just do f of b minus f of a. It's the same thing, the same result. Now we're going to back up to that little homework question I gave you, where f of z was equal to z bar squared. And we went along a straight line, and I assigned you to do it this way, and the integral along gamma 1 of f produced an answer, but the integral on gamma 2 of f plus the integral of gamma 3 of f produced a different answer. They weren't equal. Well, what does this mean? Well, it means that the theorem that we just proved can't apply here because it's supposed to be the same answer, just be beginning minus the end. So what happens here is that this f of z has to not have an antiderivative. That's kind of funky. It means that somehow the differentiability of functions control how their integrals are answered in the complex plane. We very seldom in the real plane have ever discussed or worked on functions that simply aren't integral, or functions whose derivatives are really bad. So now we're going to try to. So now let's take a look at a very specific function. And let's realize it has a problem at the origin. So I'm going to draw a picture of a domain. So I'm going to, let's take the modulus of z equals to 1/2. And out here, I'm going to take the modulus of z equal to 3. And then inside of there, I'm going to take gamma to be the modulus of z equal to 1, and I'm going to parameterize it. Well, I think that would be great to be parameterized as 1 gamma of t equals 1 times e to the I t, and t varies between 0 and 2 pi. So it takes about 6 seconds to walk around this circle. Now, this region that I'm going to work with is between these two, and f of z is differentiable on this region. It's a very nice function. Now, I'm going to integrate f around that region. Around that gamma, sorry. So I'm going to do the integral of 1 over z dz on gamma. Now, the parametrization is e to the it, so it's going to be from 0 to 2 pi, 1 over e to the it, that's 1 over z, with gamma of t plugged in. Now I have to do it times gamma prime of t, which is I e to the it dt. Now these cancel, and why I get, lo and behold, 2 pi I. So to go around this circle here, the integral is 2 pi I. Now let's just go back to that theorem that we had. That one theorem said that if f has an antiderivative on this region, then the answer would be, well, let's just recall, if f of z has a capital F of z, where f prime of z was 1 over z on d inside of the complexes, and our d, if you remember what I drew, was this region, then the integral of f over gamma would be the end minus the start, but that circle began, went around, and ended. That would equal to 0. So that means, well, clearly our domain is inside the complex plane. Clearly I parameterized correctly. The problem is there can't be an antiderivative for 1 over z. Now let's recall how we worked with the logarithm. When we did the log of z, and we discovered that the log of z prime was 1 over z, there was one basic fact that was required for that. And that was we removed a bad problem with the logarithm, and that is right here. That is not in the domain of log of z. But didn't our integral that I was just doing for 1 over z, didn't that interval include a path? I went around the circle and I crossed that point? The answer is yes, it did. So guess what? That little slice on log of z actually caused a problem for 1 over z. it is no longer a derivative of log z in the region in which it was defined for that path. So you really want to know, when you take antiderivatives, the domain in which something is defined over. 1 over z only has a problem at 0. Log of z in the reals only has a problem at 0. But in the complex plane, it has a greater problem. It has a problem all over here. And this is the first fairly significant deviation from the reals, that some subtlety and work has to be done. It just points out that learning about the log of z was not as easy as it may have appeared. All right, now we're ready to do what is called the indefinite integral in a way that produces a function as a result rather than a complex number. Up to this point, we were doing the integral over gamma of f, and this was a complex number. In addition, we could talk about the derivative of a function to get little f, and if that was done on the correct domain inside of the complex numbers, then the integral of f would be f of a end minus f of a start, again on a path. What would be nice is if we had some statement about some antiderivative that produces a function as a value. So let's do this one. This is a theorem. It's 415. So here we go. G is contained inside of the complex number as a region. And again, that requires that little disk inside of there. And let f mapping into the complex function, and it's a continuous, and the integral of gamma of f is equal to 0 for any closed piecewise smooth gamma. Now, this is not so crazy. Here's some region called G, and here's a curve inside of G, and we just to say the integral of that is 0. So it looks like no matter which one we do, we have what appears to be that integral is 0, which if it had an antiderivative, it would always be f of start minus f of n minus f of start, which would be 0. This seems to be characterizing functions that should have an antiderivative. Well, then f of z, which is the integral over f on gamma of z, where z naught is an element of G, and so is z, and gamma of beginning value a is equal to z naught, and gamma of the ending value is equal to some fixed point z. In other words, we're not going to do a complete circuit, we're just going to go from z naught to z. So we are going to let the last value be indefinite, and we're going to define that final integral then as capital F of z. And guess what? Then f of z prime equals f of z. In fact, capital F of z is an antiderivative of the function. Now, this statement, this theorem has a lot into it. So before we prove it, it says that an antiderivative is somehow related to integrals that always produce 0 on closed paths. Let's just take a look at a consequence of that once. Integrals that produce 0 on a closed path. So let's suppose we have a function f of z, and it's the antiderivative. So f prime equals z on some region G inside of the complex plane. And here's a Z0, and we wander around to a Z1, and we wander back. So if this is gamma 1 and this is gamma 2, then gamma 1 followed by gamma 2, which I called earlier the circle plus of the gammas, the integral over the f, since it has an antiderivative on this region G, must be 0. But we know that this has got to be actually the integral over f over gamma 1. Now let's go in this direction. We could go in the other direction. It's okay. Well, no, we can't. If I said gamma 1 first and gamma 2 a second. All right, plus gamma 2 of f. So we go here and we go to there. But we get 0. So that means this minus can be minus gamma 2 of f, which now, that's minus gamma 2 is going there, and it says we get the same answer. Let's say this a different way. It seems that when we have an antiderivative, then this appears to say the integral of a path gamma 1 of the function is always equal to the integral of another path of the function, provided they both start at one point and end at the other one. This is called path independence. So functions that have a derivative, functions that have an antiderivative have a unique property in the complex plane. They are path independent. And we saw for 1 over z that failed, and we also saw that the circular path for the 1 over z did not produce 0. This is a very powerful statement, and we're going to make such use of it that integration in the complex plane is going to become very straightforward and simple. All right, your assignment. First off, we are going to make sure in chapter 4 that we do 4-4. I've done half of it. You get to do the next. 4-7 and 4-11. All right. Talk to you later.